Good afternoon, everybody. This is Mr. Steele once again here. I'm going to be working through the second lesson of that second half of Calculus BC. Today's fun morning has been filled by NFL free agent news because it's the only thing that's kind of able to distract anybody from what's going on, since pretty much the rest of the sports world is completely closed up. And otherwise, I've just been reading very sobering statistics. So, yeah, it's been fun. So instead, let me jump in and start talking about a little bit of math, because that's, again, what I do best, and that's the only thing that I can really offer while kind of self-isolating and social isolating, whatever those words happen to be. So from here, where we're going to begin with this second lesson is we're going to make a big jump. It's actually a significant jump from where we began yesterday, which simply talked about sequence convergence. And while sequence convergent is useful, and as I mentioned yesterday very briefly, actually a huge part of the kind of underpinnings of calculus, the truth is the work we're going to do is going to be much more focused on series, which are very different than sequences, even though they're, of course, related to one another. So what I want to do first is kind of establish some vocabulary, and again, just like yesterday, review the elements of series that you know, before getting truly serious. So once I reach that point, then we'll be able to jump in and go through. Just like with the first lesson focused on sequences, I've put in a whole bunch more try-its than I normally would. They're all QR code based. And thank you for the people who pointed out the mistake in the first ones I posted yesterday. So having said that, my goal is to get you through this lecture and talk through the idea of series convergence, connecting it to sequences and trying to connect it to this idea of something called a sequence of partial sums, and then eventually getting you to determine the convergence of an actual series rather than just a sequence by the end of this thing. And of course, as soon as I started recording, the garbage men are here, which is a good thing. It's nice to know there's that normalcy of garbage people still working, but at the same time, kind of funny sound-wise. So either way, let's jump in and kind of talk about what we got here. So as it says, first thing I've noted in notes 24 here is I've mentioned that a sequence is an ordered list of numbers. That's a really important thing to talk about right off the bat because, of course, that's what we looked at before. The notation we typically use for a sequence is we use those curly brackets and we say, well, the sequence itself is going to be a list of numbers. Maybe that list of numbers would be 5, then 8, then 11, then 14, then 17, and maybe it goes on for a while afterwards. The sequence I've just written, by the way, is in fact an arithmetic sequence, which we talked about yesterday as being a sequence in which there's a constant difference between consecutive terms, meaning that you add the same thing over and over again to get further and further in terms of the sequence. So again, sequences, that was yesterday. Today we're going to try to bridge that forward into something a little bit different. So as you can see, the next word up there is series, and in fact that's going to be our focus from here on out. And a series is based on a sequence, but it's not the exact same thing. It's not just a list of numbers anymore. So a series is the sum. And again, the word sum means that you're addition. It's addition. You're adding things together. And it's the sum of the terms of a sequence. So some would say that the difference between a series and a sequence is just a bunch of commas are replaced with addition signs or subtraction signs, depending on the case may be. So in fact, if we wanted to look at the series that we saw up above, we could transform it into a series. Excuse me. Transform it into a series just by adding the terms together. So in this case, we'd have 5 plus 8 plus 11 plus 14 plus 17, and then onward as far as we wanted to actually go. As far as notations that we might offer for this, if that was indeed a sub n that represent the terms of that sequence, we could talk about this as being the sum of the terms of a sub n with that sigma sign, that big sideways m, I guess you could call it, the sigma. And of course, then we could say that we were going to add from the first of those terms and then up to infinity, because of course we just put a dot 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 at the end. Those ellipses indicate that we'll keep adding more and more terms of the sequence and keep moving further and further forward. So having said that, that is what we're going to be focusing our attention on. In fact, dare I say, almost everything after this point in this unit, and almost in this course, with the exception of Euler's method, is going to be based on series, adding up the terms of some sequence, some ordered list of numbers. So having said that, when we talk about series, there are really two different types that we could be analyzing. The first is a finite series. So a finite series would be something as clean as this. Let's see, I'll try to do it the exact same way that I did in my notes for simplicity. So basically this would be a finite series. The reason it's finite is that although we are adding a bunch of terms together, hence making it a series, we're stopping. We're picking a term in the sequence, or series, however you want to think about it, and we're saying let's stop right there and let's figure out the sum of those finite number of terms. So in this case, by the way, if you wanted to, you could say this is the same thing as the sum from 1 to, let's see, I think it's 100. Is that right? If we're starting at 3, yeah, I think so, of this guy. And this would, of course, be the same thing as that finite series. It's the first 100 terms of the sequence that are being added up together. And of course, if you're wondering how I got those things, obviously I'm doing some extra math ahead of time, and I'm also looking at my notes from past years so that way I can stay focused as I work through this, not wander too much. But again, there's a couple different ways to get there. Obviously, what I probably did was I figured out that since the common difference was 3 here, that meant that our sequence was going to be 3n, and then looking at the first expression plus 2, and then from there I just figured out that 302 is equal to 3n plus 2 if n equals 100. So again, there were ways to get there, but again, that's not our focus. That's sequence work we're really more interested in. Having said that though, a finite series is not actually going to be the major focus for us. Instead, we're going to focus more on infinite series. So in this case, all we do is we really write out the exact same thing we saw in the previous piece about finite series, but instead of adding something afterwards, we just kind of trail off into the night. Because, of course, we're going to go on to infinity. We're going to add up an infinite number of terms for this particular thing. As far as notationally, it doesn't look very different. In fact, because that 100 has 2 zeros, it almost looks exactly the same if you ignore that 1. But basically, we just have the terms from the first to the infinitieth? Close enough. And the idea would be we just keep adding terms on forever. Now, finite series are perfectly fine. As I said, they're perfectly fine, but of course it's pretty easy to figure it out. Although there might be a lot of terms, there are very clean ways that we can determine the sum of a finite series. Whereas with infinite series, obviously adding up all infinity terms would take us our entire lives. So that's not necessarily a good option for us. And instead we'll need to develop other techniques to determine whether or not a series will do things like converge or diverge. So that's going to be our focus for the lesson here. Before we get there though, as I mentioned, since we're just talking about vocabulary, I wanted to bring back in some work you've done before just the same, just to kind of give you some grounding in the work of series as opposed to just sequences. So in here, as we talked about yesterday, there were 2 types of sequences that were really commonly discussed when you first worked through sequences. Those sequence types were arithmetic and geometric, which had specifically patterns of addition and multiplication respectively. The nice thing is if you translate those into series and talk about things like an arithmetic series or a geometric series, there are formulas, at least for finite series. So in fact, I should probably highlight that here you're just going to see the formulas for finite series. For infinite series, we'll do a little bit more work and talk about that in just a little bit. So the first one I want to talk about is arithmetic series where the terms are sequences who have constant differences or common differences between their consecutive terms. And the formula to figure out the sum of the first n terms of an arithmetic series is basically take the number of terms divided by 2 and then multiply times the sum of the first term and the nth term, sometimes called the last term in the finite series. Excuse me. So having mentioned that, there's our arithmetic series formula. But before we go on, just because I find this really interesting, there's actually kind of I found this one memorable because of a story that one of my teachers told me in high school. So the story went like this. There was a guy, he was a bright guy, he turned into one of the greatest mathematicians of all time, and he was taking classes, or he was learning in his one-room schoolroom, where of course the students were at different levels, different mathematical levels, obviously. Here you've got someone, his name is Carl Friedrich Gauss, by the way. If you've ever done matrix work before, you've done Gaussian elimination. His name shows up a lot in statistics as well, so some of you might know him from there. But as the story goes, Gauss was a precocious pupil who asked lots of questions because he was just brilliant. He knew a lot, he was interested in a lot, and he explored a lot of things mathematically in particular. So one day his teacher, tired of trying to answer questions from this, whiny little kid with that fun little hat, just kind of went, I'll give him something to do, give him some busy work, as teachers sometimes do, to just keep him busy and keep him out of my hair so that the teacher could do their own work and take care of the other students. So the teacher, thinking they were clever, assigned little Carl Friedrich Gauss the task of adding up the first 100 positive integers. So adding up 1 plus 2 plus 3 plus 4 plus 5 plus 6, ... on forever, plus 99 plus 100. So this teacher surely thought this was a brilliant use of time. It would totally distract Gauss for a long time. But of course, as the story goes, and as you'll be able to figure out really fast here in just a second, it took Gauss seconds to finish the problem, and immediately he was back in the teacher's hair, because Gauss had observed something kind of cool about arithmetic series. So what I want to do to point this out for you, and I'm going to try to do this the same way I would normally, I want to point out something kind of interesting here that might not be the first thing you notice. So we have 1 plus 2 plus 3 plus a bunch of other numbers plus 98 plus 99 plus 100. So bear with me for a second. What is the sum of 1 and 100? 101. Yep, it is. Like the number of Dalmatians, 101. So very true. Next, let me ask you this. What is the sum of 2 and 99? 101. Yes, also like the Dalmatians. And then let's try the next ones. So what about 3 and 98? 101. Yeah, it turns out that one's also like the Dalmatians. There are a lot of Dalmatians here. Kind of Cruella de Vil would be in heaven, as opposed to where she might be otherwise. So in any event, what you might notice here is that the sum of the first and the last is equal to the sum of the second and the second to last, and is equal to the sum of the third and the third to the last. That's just basically true. There's some cool ways to illustrate why, but it has to do with the number of common differences that are being included in each one. Each one ends up being the same. Some have more at the beginning, and some have less at the end then, and they all balance out. So what this shows, or what it was that Gauss did then, was if he wanted to find the sum of those first 100 positive integers, what he realized was that the sum of each pair, either first and last, second and second to last, third and third to last, was the same value, in this case 101. And then because there were 100 numbers that were each paired up, there were 50 101s to add together. And this is actually a pretty clean multiplication. 50 times 100 is 5,000, plus another 50 is 50/50. And so that is, according to legend, a mathematical legend, the value that Gauss was able to present to his teacher that proved that it was there. And of course, this works for any arithmetic series, not just ones where the common difference is 1 or where you're counting up from 1 to 100. You can try with any sort of list of numbers and you'll get the same value. So just kind of a neat little thing to point out there. Again, not super essential. It's not something that's necessarily going to be tested on, but it's nice to be recalled where that story comes from, and because I figure it's kind of an entertaining story. Now, in addition to arithmetic, we also talked about geometric, and I'm not going to demonstrate anything for this geometric pattern thing that you're about to see, but I'll just at least point out that it's out there. Basically, for a geometric series, there is also a finite series sum formula. In this case, that series sum formula is the first term times 1 minus the common ratio to the nth power, all divided by 1 minus r. And again, as I said, we're not going to necessarily work our way through this, although if you do try it in just a few moments, you're welcome to test it out and get a feel for it. But again, this is just something else. There's actually neat little proof that involves adding multiples of things to one another. But again, it's not my focus. I just wanted to kind of point it out that it's there. And then remind you that we will come back to geometric series, but the infinite variety in the next lesson after this one. So just know there's some kind of cool stuff. Again, this is stuff you probably saw in your Math 3 class, possibly in pre-cal. If not, hey, it's not too crazy to get to. There are some formulas here, and you can look things up online if you're interested in a little bit greater depth of that exploration. Having said that, as I mentioned, I'm trying to do a few more frequent try-its. Now, I will say that I don't necessarily recommend that I don't feel like you need to do this to be able to understand the calculus at all. It's just kind of a nice pausing point. And again, I'm trying to get into this rhythm of every few minutes breaking up the lesson with a try it so that you have an opportunity to do a little bit of math alongside the same way, especially because you're not able to answer questions in real time here. If you were, that would be a really advanced technology thing. But, I'm just not a fancy video game streamer that can run things live. I'm not sure you'd want me to run these things live anyway. So, having said that, if you're interested in a try it, here is one such try it you could work through that lets you look at finite, arithmetic, and geometric series sums. But again, we're going to move on pretty quickly from here. So again, it's up to you. Feel free. And again, the links, just like the last one, the links are also in the video description should you choose to look there as well. Well, having looked at that try it possibly or possibly not, we've talked a little bit about series in general, but we focused our attention on finite series. As I said, though, that's a small thing in the grand scheme of things, so I want to move our attention instead to infinite series, and in particular to start thinking about whether or not a series converges or diverges, meaning that if we add up more and more terms of the series, does it seem like we're approaching some finite sum, or does it appear that it's going to infinity or to some non-existent thing altogether? So to start things off, just as kind of an exploration and kind of a thinking activity, I want to start by looking at a particular series and trying to reason out some intuition about whether it should converge or diverge. And again, at this point, I should also be able to use Desmos in this just a little bit, so that way I can, again, kind of illustrate some things a little bit differently too. So in here, what I've asked is the question, will the series from 1 to infinity, so in other words, an infinite series, of terms of the sequence 2n minus 1 converge or diverge? So to kick things off, I think it would be beneficial just to start by writing out a few of those terms of the sequence. So let's do this. I'm going to pretend that I just wrote that by changing the color. Hey, look, I just wrote that. Cool, good steal. Okay, so in here what I want to do then is I want to write out a couple terms. So of course the first term would be if I plug in 1 right here. 2 times 1 is 2, minus 1 is 1. If I plug in 2, I'll get 2 times 2 or 4, minus 1 is 3. If I plug in 3, I get 6 minus 1 is 5. And at this point, I can see very clearly that this is definitely arithmetic. Truthfully, I could probably see that just from looking at the expression for the rule. But what I see is the sum of odd integers, or even better yet, odd positive integers. So there is what we're looking at. This is our series. So the question should be, does this series appear like it's going to converge or diverge? Now, in a few days, you'll know instantly that this series is one of those two things. But to get there, it can sometimes help to just kind of think about what's happening with our sums. So first, our sum is 1. After that, our sum is 4. After that, our sum is 9. After that, our sum is 16. By the way, it's kind of cool. I don't know if you're noticing, but we're getting squared integers. So 16. If we go further, we get a sum of 25. What I'm noticing is that our sum keeps getting bigger and bigger. So at this point, if we try to think about this a little bit, as we add more and more terms, or as we add additional terms to our series, what we're seeing is that the sum's just growing and growing and growing and growing and growing. At least it seems that way. So it would suggest that this series is going to diverge. At least that's the thought that I have based on that kind of intuitive thinking here. As we add more terms, our series sum just keeps growing. And since it keeps growing, unfortunately, that means it's not going to approach anything. Now, having said that, because the series sum is getting bigger and bigger, and we want to say that the series diverges, we need something that's a little more formal. And thinking back to yesterday, the only work that we've done with convergence and divergence, outside of improper integrals, of course, was simply looking at sequences. So what I want to establish here is something a little bit different. I want to look at a sequence of sums, in a sense. But we're not going to have the entire sums. We're going to have what's called sequences of partial sums. We'll look at what the sum is after 1 term, after 2 terms, after 3 terms, after 4 terms, and we'll try to see if there's a pattern in those mini sums. Yeah, there's a word. I shouldn't have called it the formal name, but those mini sums. What I mean is this. Let's go down here and take a look. So if I want to calculate the sum of the first 1 terms of the sequence, that's going to be the same thing as a sub 1. And in our series, that's just going to be 1. So it's just 1. After that, if we want to talk about the second sum, that's going to be the sum of a sub 1 and a sub 2. Looking here, that's going to be 1 plus 3, which is equal to 4. taking it a step further, if we want to talk about s sub 3, we could of course say that that's a sub 1 plus a sub 2 plus a sub 3. That's going to be 1 plus 3 plus 5, which we can see clearly is 9. And then at this point, though, if I want to talk about further partial sums, it might be worth pointing out that really what we're doing here is if we want to talk about the fourth sum, if we want to talk about the sum of the first 4 terms, we can really just take the sum of the first 3 terms and then add that 4th term to it, because those first 3 are going to add up to the same value anyway. So s sub 3 plus a sub 4 is going to be the 9 that we saw previously, plus the 4th term, which was 7, which gives us 16. 9 plus 7 is 16. So having done that, what we now have is we're noticing that there seems to be this sequence of things that's here. And in fact, I would hope that based on what's here and based on some of the information I kind of let slip earlier, if we wanted to try to ask you to predict what the sum of the first n terms was going to be, we'll take a look at what each one of these things was. Those sums thus far have been 1 squared, 2 squared, 3 squared, 4 squared. We even mentioned earlier that if we add 9, or if we add the next term 11, we'll get up even further. Sorry, did I do this right? Oh yeah, the next term would be 9. If we add that next term, we would have 5 squared. So I'm hoping that you're okay with me saying that it looks like the sum of the first n terms is going to be n squared. Now, having said that, what we've really just done is we've actually just found a way to transform sums and series into actually a sort of sequence that we might be able to analyze the behavior of. So what I'm going to present to you is this thing. We're going to look at the partial sums of this series that we have up top as a sequence s sub n. The first term will be s sub 1, which we saw was 1. The second term will be 4. The third term will be 9. The fourth term will be 16. And as we said, if we keep going on, that nth term is going to be n squared. So basically what we now have is a sequence, and we have a description for the general term, or we have the rule for this particular sequence. So if we're curious about where the sum is actually going, we can do the same work we did yesterday. We can check if the sum or the sequence of mini-sums converges by taking the limit as n goes to infinity of s sub n. And in this case, since we just saw that the limit is n, or s sub n is basically the same thing as n squared, we can see that that approaches infinity squared, which is infinity. And having said that, what we just saw is our sequence s sub n, the sequence of those mini sums, is going to diverge. And of course, if that sequence diverges, that's just confirmation of what we were seeing before. As we add more and more terms, our sum just gets bigger and bigger. And so that's the same thing as saying that this series from 1 to infinity of 2n minus 1 is going to diverge as well. So basically, we have our conclusion. The way we did it was we found a way to bridge sums and series into the world of sequences, so we could use the same tools that we developed yesterday. We found a way to talk about the sequence of mini-sums, like only part of the entire sum, but slowly adding one term at a time to develop a sequence for us to look at. Now again, I'm dropping all sorts of terminology, but I want to do one more quick little exploration, because in your mind, after seeing this example, you might think, well, gosh, of course, anytime you add up more and more terms, they're just going to keep giving you a larger and larger sum. There's no way that a series could ever converge if it's infinite. And the answer to that is, well, not quite. So what I've got here is a different series. In this case, we're adding up terms of the geometric series, the infinite geometric series, I might add, 1/2 to the n. So those terms are 1/2 plus 1/4 plus 1/8 plus 1/16, blah, 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 over and over and over again. And our question is, does this converge? And in your mind, like, you might already have good intuition, or you might remember some information about infinite geometric series. But the truth is, kind of the cool thing here is that we can find what's happening with the sum if we want to, or we can also visualize this very geometrically. So in fact, let me take this rectangle right here. Like, this is a rectangle, like, you know, if I erase a side, it's a rectangle. So what I'm going to do here is I'm going to fill in parts of the rectangle corresponding to terms of this particular series. Since, again, we're just adding up these things, let's just see what happens when we add up 1/2 So there's 1/2. There's 1/4. There's 1/8. Notice that this is very easy for me to do because it's just half of whatever remains every time. There's a 16th. There's a 32nd. There's a 64th. There's a 1/128th. There's a 1/256th. There's a 1/512th. Are you noticing something happening here? I'm hoping that you are. What it looks like in this case is that we're doing something a little bit different. And this looks to me like as we add more and more terms, we slowly fill up the entire rectangle. Fills rectangle. And although it's kind of weird to think about, we might not think about like a value of a rectangle as being a particular number, we called this side half of the rectangle and this 1/4 of the rectangle. So it looks like slowly over time, we're approaching a full rectangle. So in a sense, if we want to say this, I would say that this suggests that the sum of this series converges. And I'll say even more that it seems like it converges to the value 1. We're slowly filling up that entire rectangle as we go. Truth is, though, if we look at those mini sums in the same way we did on the previous page, we can actually get a similar conclusion, but a little more substantial. Because again, what we can do is we can try to find a sequence that describes what these sums are as we add more and more terms of the sequence, or into the series. So first of all, if we look at this, s sub 1 is going to be 1/2. S sub 2, which is going to be 1/2 plus 1/4. Again, I'm going to do some fraction work in my head. Hopefully that's okay. If you'd rather not see me do this heavy duty style. That's 2/4 plus 1/4, which is 3/4. If I go to s sub 3, that's going to be 3/4 from the first two plus 1/8. If we combine that together, we're going to have, let's see, 6/8 plus 1/8 is 7/8. If we go to the fourth sum, that'll be 7/8 plus 1/16. Maybe you're starting to see a pattern here. I'm not sure if you are or not, but let's see. This will be 14/16 plus 1/16 is 15/16. Let's go one more just because we're doing okay. That'll be the first four sum plus 1/32. That's going to be 30/32 plus 1/32, which is 31/32. So in looking here, I'm going to go ahead and just draw this kind of up to the side. What I want to point out is it looks to me like we have another sequence of these mini series sums, or these mini sums, sequence of mini sums. I just want to call it the sequence of partial sums. That's what it's called, but I'm trying to prolong it as much as possible. So let's take a look at this sequence we've just created. It has the terms 1/2, 3/4, 7/8, 15/16. Again, each of these represents the sum of a certain number of terms. 1 term, 2 terms, 3 terms, 4 terms, blah, blah, blah. And then our fifth, the sum of the first 5 terms was 31/32. So this is our sequence of these mini sums. The question is, can we describe that sequence in some way? And I'd say that the answer is yes. Take a look at the denominators. 2, 4, 8, 16, 32. So can you think of a way to generate that particular list of numbers? Yeah, I'm thinking the answer is yes. I'm thinking that's just 2 to the n. 2 to the first, 2 to the second, 2 to the third, 2 to the fourth. We're just multiplying 2 over and over again. So the denominator is perfectly geometric. And the numerator might not jump out at you right away, but 1 is 1 less than 2, 3 is 1 less than 4, 7 is 1 less than 8, 15 is 1 less than 16, 31 is 1 less than 32. It looks like it's just our denominator minus 1. So in fact, I would argue that we've actually just found a way to describe the nth partial sum of this particular series. So looks really good to me. Looks like we're in really good shape. Because remember, since we're thinking of this as a sequence, we can then say things, or we can analyze things just like we would sequences. Let's see what this sequence of mini sums is doing as n goes to infinity. So in this case, that's the same thing as the limit as n goes to infinity of 2 to the n minus 1 over 2 to the n. Now, depending on how you approach things, you can do this a lot of different ways. I might actually, well, there's a couple different ways you could do this. I might point out that kind of a clever algebraic way to do this would be to separate this into 2 separate fractions. This is the same thing as 2 to the n over 2 to the n, which is just 1 minus 1 over 2 to the n. And if you take and see what this thing does is it goes to infinity, we get 1 minus 1 over 2 to the infinity, and that is, of course, equal to 1. So what that shows me is that this particular series, which again, I'm going to be a lazy cheater here, it shows me that this particular series appears to converge to 1. And of course, that doesn't necessarily come as a surprise, because that whole drawing the geometric picture was all meant to show us that it looks like indeed this series goes to 1. But having said that, we now have a way to, again, use this process of using a sequence to determine whether or not a series converges or diverges. To find out whether in adding up those infinite number of terms, do you actually get a finite value, or does it just balloon up to infinity the entire time? So kind of a neat little thing to explore. Now, having said that, from here, that process we just used here is actually a really valuable process. It's not necessarily a practical one. It takes a little bit of work to write out a few partial sums and then try to see the pattern, but it does a pretty nice job of helping us construct this really powerful sum or sequence out of a series itself, like that gives us the mini sums that are there. So the name of this thing, as I've said so many times and tried so hard not to, even though it's perfectly appropriate to have used it already, that thing is called a sequence of partial sums. Basically, it's a partial sum because we're not adding up all infinity terms, we're just adding up a set number. And it's a sequence of partial sums because we're doing it in order. We're writing out the first term sum, then the first 2 term sum, then the first 3 term sum, then the first 4 term sum. It's hard to say that, it's kind of a tongue twister. And we're writing out what those sums are slowly in an ordered list, aka a sequence. So as we just talked about, what we can do is we can actually go through and construct a sequence of partial sums, figure out what a formula is that describes the nth partial sum in that sequence, and then just check to see whether or not that sequence converges or diverges, because that's a thing we know how to do, so why not do it? So up here, we're going to do that exactly the same way. So let's jump in and take a look. So as we've said a few times, maybe we just haven't thought about it in the exact same way, S sub n is going to be our notation for the sum of the first n terms. And yes, we've used it to describe other things already, but this does a really good job for us here to just kind of establish this one more time. Our difference is, in addition to calling it that, we also can think of it as what's called the nth partial sum. And you're probably realizing already this is the bulkiest part of the lecture today. So that is our partial sum. So what we want to do is we want to try to develop what the pattern is. So we're going to check a bunch of terms in order to get there. So let's do exactly that. The first partial sum, that's easy. Looking up there at the sequence, it's 3/2 because it's just the first term. So that one's pretty easy. Our second one, though, is going to be the first term plus the second term. When we add 3/2 and 1/2 together, we get 4/2, which is the same thing as 2. So getting 4/2 gives us a value of 2. So interestingly enough, good enough for us. When we go to the third partial sum, we're going to have the sum of the first 2 terms plus the third term, which is 1/4. When we add those together, we get 8/4 plus 1/4 is 9/4. Let's look at the fourth one. How far do I want to go? I'm just trying to kind of mimic what I've done in the past. Yeah, there we go. So again, following the same pattern as before, we'll take the third partial sum, and then we'll add the fourth term to it. So for us, that's going to be 9/4 plus 3/20. That's going to be the same thing as 45 over 20 plus 3 over 20, which is 48 over 20. And if we divide by 4s to get rid of that, what's that going to be? 12 over 5? Maybe that'll be useful to us. We'll see. And then last but not least, we can do the fifth partial sum. I think that's fair. That's going to be that sum we got there right above, 12 over 5, plus the fifth term, which is 1/10. That's going to be the same thing as 24 over 10 plus 1 over 10, which is 25 over 10. Also the same thing as 5/2. So you're seeing what we do first. If you're looking kind of to describe what the process is that we're doing here. Again, this isn't a huge common thing, but at the same time it is something that could pop out. The first thing that we do is we write out, and this is a pun, so I'll press the button in a second. We write out sum we write out some partial sums. The idea is we need a few partial sums to be able to see what's actually happening with the sequence of partial sums in order for us to get somewhere. So we start that off. We write out a few partial sums. We've done that. What that gives us is it gives us a sequence of partial sums that we can start to analyze. In this case, we have 3 halves, 2, 9/4, 12/5, and, oops, it's a bad draw, 5 halves. So of course our big holy grail here though would be to figure out the general term. Like what's happening here with this sequence in general. So in order to do that, like our second step in fact would be described as we need to find the pattern. Like we need to determine the sequence that describes those partial sums so that we can look to see what happens as those terms of the sequence of partial sums go further and further along as we add more and more terms to the series. So in here I will admit that this one's pretty tough. But something that caught my eye here, and again, this might not immediately have jumped out at you because of how we were doing this through, but what I noticed was that as I was looking at these expressions, the denominators were 2, well then 1, and then went 4, 5. So my thought here is, this is just a thought, but I think it's going to work, is that if this denominator was 3, then we might have a nice pattern in the denominator. So what I'm going to do is I'm going to multiply up and down by 3 to rewrite that second term so it has a 3 in the denominator. Likewise, kind of coincidentally, if we go 2, 3, 4, 5, the next denominator we'd expect is 6. So I'm going to follow that same pattern. I'm going to multiply up and down by 3 on that 5th term, 1, 2, 3, 4, 5 as well, so that way I can see what those terms end up being. Having done that, we'll have 2 new versions in here. We'll have 6/3, and we'll have 15/6. So having done that, and again, I admit that's not a question I'd ask you on a test. That's a lot of intense speculation to get to there. But looking at those expressions, our denominator is now 2, 3, 4, 5, 6. That's an arithmetic pattern if I ever saw one. And then the numerator, we have 3, 6, 9, 12, 15. That's also an arithmetic pattern. In fact, what it looks like is in our denominator, we have n plus 1. And on our numerator, we're adding 3 over and over again, so 3n, and then it looks to me like 3n plus 2. And doing a quick check there, let me plug in a few. It looks really good to me. It looks like we've actually found what we were looking for. Wait, nope, that was bad. Lar. It's supposed to be 3n, because it's literally just multiples of 3. Ignore me. So having said that, we now have our general term for the sequence of partial sums. So now that we have the pattern, all that's left for us to do is to actually check the limit as n goes to infinity of that sequence, because that will tell us whether or not the sequence of partial sums converges. So in this case, what that means is we're going to take the limit as n goes to infinity of s sub n. It's the same thing as the limit as n goes to infinity of this expression we just kind of determined here through some clever problem solving. That limit, I mean, you can use L'Hopital's rule if you want to. However you do it, that limit is going to be equal to 3. And 3 is indeed a real number. 1, 2, 3. It is. Therefore, what we've just shown is that the sequence s sub n converges to 3. And that's all well and good, but the idea is since that sequence just represents what we get when we keep adding more and more terms to the series, that's equivalent to us saying that this particular series, sum from 1 to n equals 1 to infinity of a sub n, is going to converge to 3 as well. And that was the conclusion we were looking for. We now have some information to see if this is actually working. Now, having said all this, unfortunately, the way I've designed this series, I can't go into Desmos and show you that this is going to converge to 3 as we add more and more terms. But truthfully, I probably should have earlier shown you that some of those things do in fact seem to approach something. So let me just go back. Well, let's see, what else do I have here? Do I have any other opportunity I can show you this with? I don't. So I'll hold off on that part for just now. Instead, let me formalize this connection that we're seeing. because what we're using is a sequence of partial sums to determine whether or not a series converges. So whether or not a sum of a bunch of terms actually goes somewhere. So in here, like, this is sort of a theorem. It's not really, I guess, a theorem. It's just kind of an observation, but it illustrates what we've just been saying and what we've been doing. It says for an infinite series sum of a sub n, so in other words, there's a sequence a sub n and we're adding up its terms. If the sequence of partial sums converges to s, some real number, so in other words, if you check the convergence of the sequence of partial sums and it converges to a real number, then we'll say that the series converges to its sum s. So it's like saying that that sum is going to get closer and closer to a particular number as you get more and more terms added in. As it says down below too, it says if the sequence of partial sums diverges, then we'll say that the series diverges as well. So basically these two concepts are completely married to one another. They mean the same thing. And in fact, at this point, they're our only tool to determine whether a series converges or diverges. As far as like too long didn't read kind of stuff, if you want to see, you can, in other words, you can check if a series converges. So again, I probably should have written this ahead of time, but here we are. You can check whether a series converges via the limit of its sequence of partial sums. So in other words, the sequence of partial sums is a really powerful tool to determine information about whether a series converges or diverges. There we go. And you know what? Before I get to the last problem before this triad, and this has been a long chunk, let me go into Desmos really fast and illustrate, at least with one of the problems that we did earlier. Where is it? There's one. Like we said that this one seems to converge to 1. Let's just actually see for a second if that's true. So n equals 1 to k. There, just so let me fix that. Okay, we're going to take our sum. It was of 1/2 to the n. So if you'll recall, we claimed, by doing our work earlier, by looking at the sequence of partial sums, that, let's see. Oh wait, this goes by 10, so I gotta go 100. That supposedly, as we add more and more terms, this sum is going to get closer and closer to 1. Let's see if that's true. Can you see how those values of that sum are getting closer and closer to 1? Look at that. By the time we reach, was it 42? Oh, it was almost. By term 41, Desmos can't even tell the difference between the value it gets and 1. That tells you more than anything that, of course, we're going somewhere and we're converging. Take that instead with 2n plus, or sorry, it's 2n minus 1, I think was the one we looked at. So take a look at what happens as we add more and more terms here. Notice that those sums just keep getting larger and 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 larger. That's just a huge thing. Let me try something once. Oh, that's kind of cool. You can see that sum just keeps getting larger and larger. That's like telling us that the sum is growing too much. On the flip hand, or on the other hand, 1/2 to the n. Look at how that one flattens out. Just like we said, it looks like it's approaching something, and it does look like it's approaching 1. So having seen that, just kind of an interesting thing to note. Supports our work with these sequence of partial sums here. Shows us how valuable it is. Okay, the last thing we'll mention, I'll throw out here just before letting you dig in and start to work on a quick little triad, is to have you take a look at how simple it is if you actually know the sequence of partial sums. In fact, I might even say this is an unnecessary problem. So in this example, something that has popped up though before, it tells you that the sequence of partial sums s sub n is equal to 4n squared plus 5n over n squared minus 4. The question is, does the series sum converge? And the answer is, well, by having the sequence of partial sums, this is almost trivial. We take the limit as n goes to infinity of that partial sums formula. That means we're going to be evaluating the limit as n goes to infinity of 4n squared plus 5n divided by n squared minus 4. And again, whether you're using L'Hopital's rule a couple times or whether you're just recognizing patterns or using controlling term analysis, you should see that this becomes 4 over 1, which is equal to 4. And as soon as you see that a sum, the sequence of partial sums converges to a real value, we can then say that the series in the question here converges to that value as well. Meaning that if we kept adding more and more terms of the series, the sum, the total sum, would get closer and closer to 4. So again, not even really a necessary problem, it's just the gist of what we've done already. So having said that, as mentioned, here is another try it for you to work through. So there are a couple more questions. This one will probably take you a little more time just because it's using the partial sum terminology. It's asking you to do some of that more intense stuff. So if you feel like you've got the idea, maybe save that work for the assignment for this lesson, just because the assignment has a lot of this good stuff also. At the same time, if you feel like you want to kind of take a break and pause and kind of look at some of the stuff, this might be a really good, well-timed try it for you to really gauge whether or not you've got this, and make sure that you're in good position heading into the final stretch, which is really just a single skill. So anyway, I'll take a short little break here and let you work your way through this try it should you choose to. Okay. Hopefully you've had enough time to either use the QR code or click on the link if you decided to work through this try it. Hopefully you feel good about the idea of using a sequence of partial sums, because the last little chunk of the lecture is going to feature the same thing. So basically the next question we have is for a particular type of infinite series that we're going to look at, and we want to determine whether or not that particular type of series converges or diverges. So this is a topic that shows up every once in a while, but it's more kind of a clever application of the sequence of partial sums, because that's basically going to be our one tool here. We're going to see what happens with the sequence of partial sums. We'll try to write a short formula for the nth partial sum, and then use the properties of sequence convergence or divergence to see what actually happens. So what that looks like here is going to be pretty simple. Let's start out by writing out the terms, or the individual values, of each of the partial sums. So for the first one, if I look at the first partial sum for this sequence, 1 over n minus 1 over n plus 1, that'll be 1 over 1 minus 1 over 1 plus 1. It's clearly going to be 1 minus 1/2. Now, you might be tempted to simplify that to 1/2, because of course it's equal to 1/2. But bear with me for a second. Something interesting is going to happen here. This is a special type of series. So if we want to do s sub 2, that's going to feature two terms. It's going to be the first one, 1 minus 1/2, plus the second one, which is going to be 1/2 minus 1/3. So in other words, if we're looking at this series, or this sum, you might notice that the 1/2s go away, and we're left with just 1 minus 1/3. So make note of that. Let's look at the third partial sum. It's going to be 1 minus 1/2. Actually, let's just go with the partial sum we had before. It's going to be the second partial sum plus the third partial sum, which will be 1/3 minus 1/4. Notice once again, gonzo, we're left with our third partial sum as 1 minus 1/4. And if at this point you're not 100% convinced, let's look at one more. So the fourth one would be the sum of the first three, which is 1 minus 1/4, plus the fourth one, that would be when we plug in 4 for each of these, which would be 1/4 minus 1/5. So we have plus 1/4 minus 1/5. And one more time, we have a bunch of the intermediate terms zeroing out, and we're left with 1 minus 1/5. Now, having done this, of course, we now have an idea of where this term's going. We've got the terms 1/2, 2/3, 3/4, 4/5, but more than that, we have a nice, easy way to express what we'd call the sequence of partial sums. The nth partial sum, according to this pattern, should be 1 minus 1 over something. As far as what that over something is, take a look at the denominators here. We have, for 1, we have a denominator of 2. For 2, we have a denominator of 3. For 3, we have a denominator of 4. For 4, we have a denominator of 5. Hopefully then it's not too big a stretch to point out that it looks like our denominator is going to be n plus 1. We'll take whatever the n level is, and then we'll have n plus 1 in that denominator space. Now, having done all this work already, we're actually ready to finish off this problem. This is going to be, according to what we see, it looks like then our series will converge to whatever value we get if we take the limit as n goes to infinity of s sub n. Looking in here, the limit as n goes to infinity of our expression 1 minus 1 over n plus 1 is going to be equal to, or I'll do it right below, there's a little more room. It's going to be equal to 1 minus 1 over infinity. It's the same thing as 1 minus 0, which is equal to 1. So according to this, it looks like that series that we were asked to examine, this series, and again, I'll just cheat here and write it in, it looks like this series converges to 1. So that means as we add more and more terms, theoretically, this series, or the sum of the terms of this sequence, should get closer and closer to 1. Well, let's use Desmos once and see if that's true. So I'll get rid of this for a moment. Let's go back to K. Our series was 1 over n minus 1 over n plus 1, if memory serves. Let's check and make sure that was true. Maybe I'm misremembering. There it is. So there's our sequence. So the question is, what does that sum right here get closer and closer to as we add more and more terms? So obviously you can see every once in a while it kind of becomes small. We're at 0.97, 0.98, yeah, you can see. I mean, I feel like it's reasonable. Let's go up to 500. Maybe this will still let me do it. 0.996, 0.997, 0.998. Yeah, I'm trusting that you're seeing that this does in fact look like it's getting closer and closer to 1. And in fact, if we wanted to do it this way, put that in there, once again, we can see that it does in fact look like it's flatlining. Looks like it's asymptotic and approaching a value that I'd describe as 1. That looked like a pretty safe bet to describe this guy. So in other words, it looks like we've, oops, don't need another QR code, don't need those, don't need those, don't need that. Jeez, there it is. Looks like we are in fact converging to 1. So this type of series was just a sequence of partial sums opportunity, but the way that the terms kind of zeroed each other out, the way they added up to 0 and undid one another, makes it a very specific and kind of common type of series. This is called a telescoping series. And as it says in here, a telescoping series has intermediate terms of the series zeroing out, leaving a simple expression for the sequence of partial sums. So if you're wondering why they call it a telescoping series, considering telescopes usually look to the stars and look all the way out, it's because of a true kind of simpler version of the telescope that's used by people on boats. Let's see if this works. So two very famous boating peoples, Captain Jack Sparrow, and I actually don't remember his name. That's not a good sign. Only remember Jack Sparrow. Jack Skellington? No, that's a different movie. Maybe I'll have to watch these movies during this strange time. But in any event, those telescopes, like, they come out really long, but they start really small. You basically stretch them out, and then those lenses appear in sequence, and they allow you to kind of make something bigger. So in here, the reason this is called a telescoping series, because the series is a lot like a telescope, where you can close it up really tightly and kind of simplify the shape just a little bit. So these things, the name to know is, of course, the one you see right up there. These are telescoping series. And that's what we're going to be looking at here, is evaluating telescoping series. Now, of course, most telescoping series, if they have a simple formula like this one and they're written out as a difference of two terms, they're very easy to calculate. But sometimes you're not able to actually see that formula, that nice telescoping pattern, right off the bat. So this next example will be an opportunity for you to recall a topic of Calculus BC from the first half that actually lets you see how nicely telescoping these series are. So consider this just kind of an extra example to let you see how this works through. So if you feel really good about it and you want to go forward, go for it. But this example is typically something that throws people off a little bit. So let's talk just a bit. So it asks us to determine the convergence of this guy. Later on, we'll be able to use something called the limit comparison test to very quickly see that the series converges. But in this case, we don't want to just know that the series converges. If it's telescoping, which it is, we should be able to figure out what it telescopes to. Like, what is that sum that it's going to converge to as we go on forever? In fact, let's pull something up here really fast. Let's see. This is 6 over n squared plus 8n plus 15, I think was what it was there. There it is. Like, what does it look like it's getting closer and closer to? 1.33 something, 1.34, something like that. So not necessarily conclusive, but it does look like it's approaching something. And if we do that same kind of visual trick that I used earlier, it definitely looks like it's asymptoting as well. So let's figure out what this converges to. So the problem here, as mentioned, is that this doesn't look like a telescoping series. Telescoping series is obvious when you have something like this, two individual rational expressions that are being subtracted. In this case, I don't see it there. So the question is, how can we get there? And the answer is we need something that will break this up. So what we're really thinking at this point is, gosh darn it, I just wish, oh, I wish so much, that this expression was equal to a over something plus b over something. And in fact, that denominator, which if we so desired, we could factors nicely into n plus 3, n plus 5. So what I want is I want this expression to be equal to the sum of two simpler, cleaner rational expressions. So what I need to do in order to get there is I need to use partial fractions. Interesting that it's the word partial once again. Hopefully you're partial to partial fractions. So it's probably been a while since you did heavy-duty partial fractions, but it's not a particularly difficult skill to retain. What we do basically is we imagine fraction busting the entire thing and multiplying through by that denominator. That leaves us with the equation 6 equals a times n plus 5 plus b times n plus 3. Looking at those expressions, if we want to plug in values of n, we want to choose ones that will simplify our piece, so we pick really convenient values of n. Specifically, I'm going to first choose n equals negative 5. When I plug in n equals negative 5, I get 6 equals 0, and then plus b times negative 2. Given that information, that means that b is equal to negative 3. Likewise, we can plug in negative 3 to zero out one of those factors and clean up our equation, or find a really convenient version of our equation. We'll get, in this case, 6 equals 2a plus 0, because negative 3 plus 3 is 0, times b is going to be 0. And that tells us that a is going to be equal to 3 as well. The reason that's so huge is it means that our series can actually be written instead as the sum from the first term to the infinitieth term of what looks like 3 over n plus 3 minus 3 over n plus 5. And that has a form that looks much more like this telescoping expression that we're looking for. And those denominators are the same, so there's some potential that some of those intermediate terms might actually zero out. So having found that information, let's go through and actually work our way through it. Let's see if we can... Wait, did it just steal the parenthesis? Are you kidding me? Oh, did you notice that? It really... There, that... No, really? That's what it wants to do. I just want to move this to the side so I had a little more room. So, who am I to say? Okay, I'm going to do it that way. I hate when the computer fights me like this. It's just a waste of time. But in any event, voila. So there is our stuff. Okay, so having done that, we now want to go ahead and construct a sequence of partial sums. We want to see what this one's doing. And again, this is usually the hard part for people. It's not usually the partial fractions, honestly, where people struggle. So in looking at here, we're going to construct the partial sums. So first, if we plug in s sub 1, we need to be careful with this and make sure that we clean it up as much as we can. S sub 1 is going to be 3 over 1 plus 3 minus 3 over 1 plus 5, which is 3/6. Now, as you saw in the earlier example, I'm not going to simplify this at all. I'm just going to leave it as is. I just want to go far enough so I can see what's left over here. For s sub 2, we'll have 3/4 minus 3/6 plus what we get when we plug in n equals 2, which is 3/5 minus 3/7. So notice, sad panda, nothing's canceled itself out. Nothing's canceled yet. So too bad for us. Let's try s sub 3 though. So we have 3/4 minus 3/6 plus 3/5 minus 3/7. When we plug in n equals 3, we get a over 3 plus 3, or sorry, we get 3 over 3 plus 3, which is 3/6. Aha! minus 3 over 3 plus 5, which is 3/8. So now finally, it appears that we've got some stuff zeroing out. We've got those two terms gone. So if you want to, you could go one step further just to kind of confirm the feeling. I usually do go about 4 terms, or 4 partial sums. I'm going to cheat a little bit here. In fact, why don't I just get rid of that? Watch this. I am such a clever guy. I'm just going to change it so that there's no red circles yet. Although actually the red circles will stick around. I'll change it so it says S sub 4. And then I'll just add the next term, which is going to be 3/7 minus 3/9. Okay, so in looking here, does anything else zero out? And the answer is, oh yes, it does. 3/7 and minus 3/7 go to 0. So it's at this point where I say that we should be able to kind of draw our conclusion. So I want to look at what S sub n should be expected to be equal to. So looking in here, there are 2 terms that did not zero out. And in fact, because our denominators are continuing to get bigger, we're never going to get 3/4 and 3/5 gone. So that tells me my nth partial sum is going to be 3/4 plus 3/5. Then outside of those guys, there are a couple other values here that have also stuck around. We've got 3/8 and 3/9. Now, if we went another term out, the 3/8 would go away, and if we went another term out, the 3/9 would go away, and would be replaced with something else. But what I want is a general description of those terms for when we have n, not just 4 or 3 or something else. So let's think about this. How do you get from 4 to 8, or how do you get to 8 from 4? You go n plus 4. Likewise, how do you get from 4 to 9? You go n plus 5. So it looks to me like that should solve our problem. If you want to check, we could also go up one step higher and we could look at the third partial sum. So there we have 3/4 plus 3/5. Then we have 3 over 3 plus 4 minus 3 over 3 plus 5. So it looks to me like we have found the correct formula for our sequence of partial sums. Now that we have it, I don't know why did I choose that color. Let's go with turquoise. I haven't used that in this lesson. Okay, now that we have that, we can say that what we really want is we want to figure out whether or not this series is converging to something. Our limit should be the limit as n goes to infinity of S sub n, and S sub n is that 3/4 plus 3/5 minus 3 over n plus 4 minus 3 over n plus 5. Having done those together, we can see very quickly that our sum is going to be equal to 3/4 plus 3/5 and then minus 3 over infinity 2 separate times. Both of those will go to 0. We'll be left with our sum as just 3/4 plus 3/5. That's 15/20 plus 12/20, which is equal to 27 over 20. So it looks to me like our series is in fact converging to 27 over 20 because its sequence of partial sums of this telescoping series is converging to 27 over 20. Now we had a value that was up there. Let's see if this is reasonably close. What is 27 over 20? 1.35. The question would be, can you believe that this series is getting closer and closer to 1.35? And I would say that, yeah, it's not quite there at 1,000, but I don't know, 10,000 terms? Are we getting closer and closer to 1.35? Yeah, it does look that way. That looks like a fair description, so it looks like we found an accurate value. And again, if you didn't have Desmos, obviously it's fine. You can just look at the values here. But there is our value. And we took advantage of the telescoping property that we unveiled using partial fractions. By giving us that structure, we could construct a sequence of partial sums and then develop a formula for that sequence of partial sums that revealed the value to which this particular series was converging. So, a lot of big stuff there. Very computational and small in the grand scheme of things, but a lot of really good algebra and good mathematical thinking involved. So now having said that, I do have a short triad for you to work through, just in case, because I know that this telescoping series question is one that people typically stress about prior to exams. So in fact, just pointed out that we're looking at this one. So if you're recognizing the structure from the previous problem, you would have to use, You'd have to use partial fractions first before you could get to the actual sum here. But I think this is a really good opportunity for you to just kind of check your work really quickly before you work on the assignment. The assignment's not particularly involved. But this is a good opportunity for you to check out telescoping series and kind of play through that work the same way as you might otherwise. So feel free. I'm not going to pause in this case. Like, obviously it doesn't really pause in the video anyway, but feel free to take a look either through the QR code or through the link in the video description if you'd like to. Having said that, since we've looked at a bunch of different stuff using the sequence of partial sums, like, here's kind of the state of the game as we wrap things up. This is the final little piece that I've got in this lesson. Basically, if your series is telescoping, or we have the ability to construct a sequence of partial sums with a formula that we can recognize and describe and evaluate the limit of, cool, we can find the value to which the series converges. Unfortunately, though, if it's not telescoping, or we don't have one of those like ready-made sequence of partial sums formulas, we're just stuck. Like, there's just nothing we can do. Like, we just don't have enough tools to get there. Something you could do, as it says here, is that you could start to investigate what's happening with the sequence of partial sums and try to see if maybe you get somewhere. Or you could pull out a graphing utility or something like Desmos and get an idea of where those sums are going. But that's just not informative enough. And truthfully, sometimes we're not even really interested in what the series converges to. We just kind of want to know, does the series converge? Because if it converges, that guarantees certain behaviors. And we'd be able to take advantage of those behaviors quite a bit. So after today's lecture, our focus is going to be on developing techniques that help us determine whether or not a series converges or diverges outside of the world of telescoping and sequences of partial sums. Everything we'll see after this point is borderline ridiculous as far as the sequence of partial sums formula would be. So just know that, like, if this doesn't necessarily stick, like, definitely don't give up on the unit. Obviously, we have other things for us to actually work through. But it's definitely something to think about here. Like, basically, like, what else is coming? We've got more intricate series, and basically we're going to determine all sorts of techniques. I believe there's, in fact, 8 more techniques. Maybe it's 9, maybe it's 7. I might be off by a little bit. Those techniques for us to use to determine whether or not a particular series converges or diverges. And then later on, once we know that, we'll be actually able to describe all sorts of behaviors of functions outside of the series world by transforming them into series and polynomials. So having said all that, again, just like yesterday, the last little bit kind of bogs everything down. Hopefully this has been informative and given you some good context to work through this new topic as we start to explore and turn into the true world of Calculus BC's last chunk, which focuses on series. Having said that, thank you for watching. Thank you for listening. Please stay well and stay healthy. In fact, maybe I should even point out, I noticed this on Google earlier. Not that anyone needs me to show them what is Google. I thought this was kind of nice. 5 things to help stop the coronavirus. As it says, wash your hands often. Elbow, cough into it. Okay, I guess what they're going with. Face, don't touch your face. Like, I'm not very good at that, but again, I wash my hands a lot. Stay more than 3 feet apart from other people. And if you feel sick, just don't go anywhere. So that's always a great strategy in general. So things to work through. Cool little animation as well. Having said all that, one more time, thanks for watching. Stay safe. And I'll be looking forward to talking to you remotely in this weird way once again tomorrow. Have a good night.